Welcome back, everybody. In this video, we're going to be finishing up section 9.2. So where we had left off last time was we were doing a couple of examples where we had done a hypothesis test and a confidence interval for the means of two populations. So where we're going to start here is taking a look at the situation, unlikely situation where we know actually the two population standard deviations. We saw in the last video that we were operating under the assumption that we don't know sigma 1 and sigma 2. We used the t-table, and we had a way of figuring out the degrees of freedom that went with that. If you do happen to know the two standard deviations, sigma 1 and sigma 2, really the difference is basically that you're going to use the z-table instead of t. And the formula for the test statistic looks basically the same, except there's a z, of course, instead of a t. And then down underneath the square root where you saw s1 squared and s2 squared, you're going to use those two standard deviations because you know them, right? Before, when we were using the t-distribution, we didn't have the population standard deviation, so we used the samples basically kind of in their place. Here, if you actually have the population standard deviation, you use those and then you use the z-table. Other than that, all the mechanics of the test is the same. Okay, but like I was saying before, it's really pretty unlikely that you will have the population standard deviations. Okay, so moving on then, we have another possibility, and that is where we don't know sigma 1 and sigma 2, but we are able to assume that they're the same. Like, in spite of the fact that we don't know them, we have reason to believe that they are the same. So that's what this next part is about. So that's the part of the requirement. Again, we're working with independent samples. They are simple random samples. And then once again, we need the sample sizes to be at least 30 or bigger than 30, or for the two populations to be normally distributed. Okay, so the what you need part is basically the same as before. And then what's different, or what do we have different? The test statistic looks really similar. We have again, it's a fraction. It's the difference of the two x bars minus the difference of the two mu's. And again, that's going to be hypothesized to be 0. That's our null hypothesis. What you're seeing different is for the standard deviations. Here it says SP. Before we had just plain S's for or S1 and S2 for the two sample standard deviations. Here we're going to get what's called a pooled sample variance, and the P there is for pooled, and it means putting things together. And that's calculated down here. So this SP squared is calculated by this long value here, and it's got N1 and N2 in it, and then the S1 and S2 both make up that calculation. So that's basically the big difference here is this calculation of SP squared rather than using S1 and S2 in their place. So again, we don't have the sigmas, we don't know them, but in the case where we are able to figure out that they are the same, we do make that modification and use this. One thing that I can tell you that may make your life a little easier is that you can see that SP is it's the same thing in two different places. So note that underneath the radical, then, if you factor out that SP squared, you only will need to type it into your calculator once. Then you have 1 over N1 plus 1 over N2. So that would be an alternate way of presenting that radical. And there you see the SP squared occurring only once. All right, so let's try an example. So also one other thing I'd forgotten to mention, the degrees of freedom calculation is a little funny. We add the two sample sizes together, N1 plus N2, and then subtract 2. So that's how we'll calculate our degrees of freedom here. All right, so let's try an example. So here it says a researcher wishes to determine whether the salaries of nurses employed by private hospitals are higher than those of nurses employed by government-owned hospitals. Using an alpha of 0.01, we want to test the claim that private hospitals pay more. Assume the populations are normally distributed and the population standard deviations are equal. Okay, so We're told that we can assume the populations are normally distributed, so it's okay that our n's are only 10 and 8, so that's not too bad. We're also told that we can assume that the population standard deviations are equal, which is going to be what justifies this procedure versus the first one that we did in 9.2. Okay, so where should we start? We should state the hypotheses. So we'll have a null and an alternative hypothesis. For consistency's sake, I'm going to call the private hospital people population number 1. The employees of government-owned hospitals will be population 2. So the null hypothesis is that mean salary is going to be the same for both. So mu1 is equal to mu2. And then the claim is that private hospitals pay more. So private was population 1. And so the alternative will be that mu1 is bigger than mu2. Of course, if you set this the other way and made government number 1, then it'll be mu2 bigger than mu1. Okay, but that's how that is, the way that I've set this up. This is going to be a right-tailed test. So let's go ahead and draw our picture. You may get tired of drawing the pictures. I find them helpful. It helps me get the right answers, set things up correctly, and make the right conclusions. Okay, so this is a right-tailed test. We're told to let alpha be 0.01. So we should have an area of 0.01 in our right tail. And then the next thing that we're going to need is the critical value. But in order to know that, we need to know the degrees of freedom. So the degrees of freedom will take the sum of the two sample sizes and then take away 2. So for degrees of freedom, it's going to be 10 plus 8 minus 2, and that's 16. So we need to refer now to our t-table. We're going to look under degrees of freedom 16 and then area in one tail of 0.01. So let me grab our t-table. All right, so I've got our table. We found that our degrees of freedom is going to be 16. And then this was a right-tailed test with an area of 0.01 in one tail. So in our top row, it says area in one tail. This is the 0.01 column. And we want the row for degrees of freedom 16. So that should be 2.583. Okay, so that will be our critical value. Okay, so then what's next to do is to figure out our test statistic. As part of figuring out the test statistic, we're going to need this pooled sample variance. So let's get that next. All right, so I figured out the pooled sample variance. So here, notice that the sample sizes were 10 and 8, and the formulas involve one less than that, which is why you're seeing 9s and 7s in a couple of places. We've taken the sample standard deviations and squared them in both cases. You'll notice that in the denominator, we have n1 minus 1 plus n2 minus 1. And if you simplify that, you will get n1 plus n2 minus 2, which is the same as our degrees of freedom. So that degrees of freedom is always going to end up appearing in that denominator, as it turns out. Okay, so what we need to do next, we're getting there, is we're going to assemble our t statistic. So let's do that next. All right, so going through the calculations, we ended up with a test statistic of 1.95. So how we obtained that, of course, the difference of the two sample means were given here in the table, so I just copied those down. And then down below, we have the square root of that SP squared, this pooled sample variance, times the sum of the reciprocals of the two sample sizes. So what you're seeing is what I've got written up here in brown. All right, so we ended up with a test statistic of 1.95. So then comparing that against our rejection region, it doesn't fall in the rejection region. We ended up with 1.95. And so based on that, we can fail to reject the null hypothesis. Okay, so I'll write out a conclusion on that here in a second. Here you'll notice we did do this using the critical value method. if we wanted to pay attention to the p-value method, let's think about that for a second. So once again, our degrees of freedom, we decided to use 16 for this. We're using 16 for this. 1.95. So if you look closely in the table, you're not seeing 1.95 in here, but in here we've got 2.921, 2.583, 2.12, and then 1.746. So if there was a column that included our test statistic of 1.95, it would fall in here in between columns 3 and 4. And so as far as the area in one tail, notice those are in order from smallest to largest. So the area in one tail is between, we don't know what it is, but it would be between 0.025 and 0.05. So our p-value is bigger than 0.025, but is less than 0.05. So if we had decided to do this test at the 0.05 level, we would have ended up rejecting the null hypothesis. But at the 0.01 significance level, we're failing to reject the null hypothesis. Okay, so let me go ahead and write out a conclusion. All right, so our conclusion in full then looks like that there's not enough evidence to support the claim that private hospitals pay more. Again, it may be that they actually do pay more, but at the 0.01 significance level, there's not enough evidence to support that claim. Another way of looking at it would be that that $500 difference that we saw between the two means is attributable to chance, essentially. Okay. So then I went ahead also and recomputed this without that assumption that the sigma 1 equaled to sigma 2. That is, I went ahead and did the procedure that we followed at the beginning of section 9.2. If you don't do that, then you get basically the simpler version of the test statistic. And we ended up with 2.02. For that, we would have still ended up rejecting the null hypothesis. It would have been a little higher, but still under that critical value of 2.583. Okay, all right, so that takes us to the end of this example and also to the end of this section. Let me know if you have any questions, and then have a great day.